Our idea to create a thermoelectric magnet began with a thermoelectric generator. Thermoelectric generators directly convert thermal energy to electrical energy. They are solid-state devices, which means they have no moving parts. Why does this matter? Without moving parts and mechanical losses, thermoelectric generators have the potential to reach high conversion efficiencies. This means they could be a highly efficient method of recovering waste heat from working machines. Thermoelectric generators function primarily by the Seebeck effect, a phenomenon in which a temperature gradient across the two ends of a conductor creates an electric potential difference. Thermal excitation causes electrons to diffuse from the hot end to the cold end, creating a negatively charged cold end and a positively charged hot end. This creates an electric field within the conductor, which yields a potential difference. Mathematically, the Seebeck effect is given by the equation shown, where S is the Seebeck coefficient. The potential difference is maximized by connecting multiple conductors in series. Also, dissimilar conductors must be used alternatingly, or else the voltage differences produced by opposite temperature gradients will negate each other, as shown. At this point, we decided, why not make this circuit 3D instead of 2D, making a coil instead of a zigzag pattern? Then we can make a thermoelectric magnet. Thus, we will demonstrate the presence of a magnetic field at the center of a current-carrying coil of alternating conductors.
The Seebeck effect can be difficult to characterize with analytical techniques. Thankfully, the voltage and temperature relationship is well documented and tabulated for materials using thermocouples. In our project, we used Type K thermocouple wires in the construction of our thermoelectric magnets. To evaluate the effectiveness of the magnet, the magnetic field was calculated using Ampere's law for a solenoid. The values for current were obtained in two ways. First, by measuring it directly via a multimeter, and secondly, by approximating the temperature difference between the coil ends, converting the temperature difference to a potential difference using thermocouple tables, and finally using that potential difference, the number of thermocouple conductor pairs connected in series, the measured resistance of each coil assembly, and Ohm's law. One of the thermoelectric magnets had a wooden core and the other had a carbon steel core. We expected the steel core to produce a larger magnetic field, since the relative permeability of carbon steel is 100 times larger than that of wood. The magnetic fields were calculated using the methods and equations just described. The design variables for each coil, as well as the estimated magnetic field values, are shown. Let's see if our predictions were correct in a demonstration. In conclusion, two thermoelectric magnets were successfully built and tested. The steel core coil produced a larger magnetic field than the wooden core coil. There are currently few practical uses of thermoelectric magnets. The Seebeck effect may be better applied for power generation in the form of thermoelectric generators. Nevertheless, this project successfully showcased the Seebeck effect and principles of electromagnetism.